Okay. Okay. So what we will do today is we will cover one of the main topics. One of the very probably the most important concept in operating system, which is the concept of a process. Okay. Now, what's a process? A process is an instance of a running program. What this means is, do not confuse this with a program or a program processor. When you talk about the program, you may be talking about something that's an executable, something that stays uh, uh, persistently on some like disk and etc. Sometimes, you may talk about a running program, but this is instead of a running program, you will be using the term process. Okay, and it is very important. And what they in a process, two key abstractions are provided. One of them is a logical control flow. What this means is when you have like as Onur Hoca has already told, and I also told last week, the CPU is being shared by multiple processes at any time. Okay, so if you have even if you have a single core, you run this process a bit, you put it to sleep, you run this a bit, and then this, and then this. And if you do this switching, fast and fast like this, okay, then you have the feeling that you have these two processes running at the same time. And as you know, when you write your code, you don't care. Basically, you write your code as if you have a single logical control flow, meaning that your code runs, has its own processor, and it is dedicated to that particular process all the time. Okay, so you don't have to, you never worry about sharing the CPU with other processes that are active at that time. Okay, so each process, this is the first basically abstraction, that each process thinks that it has exclusive use of the CPU. That's one. And the second one is the private virtual address space. This is, we already know this from computer organization. Each program process has this illusion that it has exclusive use of the main memory. It's not sharing it with anybody else. And as a matter of fact, in its implementation, you can see that it even has this illusion that it has much larger memory space, address space, than what is physically available on the computer. Okay, so these two key abstractions provide the basics for a process. Now, as I said, in the case of a CPU, the process executions are interleaved because we have this multitasking system. You run this a bit, stop, run this a bit, stop, and this is and so. So this then you have this illusion, and the address space management is done by the virtual memory system. So the process is essentially the operating system's abstraction for execution. And when I ask you what the process is, one simple thing is it's a program in execution. And it is different from a program because a program refers to the executable on the disk, okay? Whereas a process is also contains the state of the running application at that time. So we can define the basically a process in terms of three main components. The first one is the address space, meaning that the whole memory state address space that it has. Okay, and you can see that in this address space, it contains the code, it contains the static variables, heap, stack, and etc. All these things are in this big virtual address space. That's the first component of the process. Okay. The second one is the processor state, which is essentially the registers that we have on the CPU. Okay. What's in EAX, or RAX, RBX, RST, etc. Okay. Or like things like page table based register. These are all uh, uh, constitute the processor state. And then there's the third component, which we call the operating system resources. This is something that, we have no idea, and it will be clarified as we move on in the course. And these resources are basically refer to the data structure that are held by the operating system that is associated with the process, okay, such as open files, network sockets, and so on. So for this third one, I'd like to just clarify you a bit for this time. And imagine, for example, how do you read from a file? Well, you open the file, you get a file, an index for the file pointer, right? And then what do you get? Then you do a read. And then when you read the file, like if you're reading from a file, okay, you have a pointer, it moves a bit. And next time you read more, it moves from this location to a little bit further, right? So you have this, but in your program, you never, there is nothing that tells you where this pointer is in your file. Okay, if you're doing say reading 8 bytes or 64 bytes from this point on, and after that the next one will be different. So the operating system keeps track of this pointer in your file, okay, the file pointer in that one, and that is, for example, a structure. We call this an operating system resource. Okay, so it's a data structure that is held by the operating system on behalf of the process, and this is basically what constitutes the process. So we have 3 components: address space, processor state, and operating system resources. Now let's look at them basically a little bit in more detail. Now, in computer organization, we have learned that every process has this blank slates, which starts from 0000, so FFF, okay? This is, if you remember, this is like 48, 2 to the power 48 for 64-bit systems. And in this space, we have these, called segment resides here. Then we have initialized variables, uninitialized variables, heap, and stack. So they're all stored in this address space. And every process has been allocated a copy of this private virtual address space. Okay? So we need to basically and you can imagine that when you run your program, your initialized variables, they will change over time. Your stack grows and shrinks. You may allocate space from heap and so on. So all these things will change. So you need to, if you want to save the state of a process, you need to save everything that's in here, or this part. Okay. So this is the part that's, for example, when you do a system call, the code for that system call, it's essentially like a function call, right? Or instruction. They are stored in this region in the virtual address space. Now, those libraries are typically allocated in here. It's not shown here, but usually in this region between stack and heap, there's a place for libraries, especially the DLLs, dynamically linked libraries. They are usually marked in the user space. This is the part where you can, the code in this reserved section, they can be run only in kernel mode and when you're executing system calls. So, but you know that this is the virtual address space, meaning that all this thing here is just an illusion. And all these things are actually mapped onto the physical address space, and it's actually a much different view that we have in there. Now, when you want to save the execution state of a process, what I mean by this is, as I said, we want to simulate this following. We want to, when we are running this process, I want to stop this. I want to save all its state somewhere, okay? And then restore the state of a new one, and then execute this one a bit, and then save this, and then restore and this one, okay? So for this, you need to be able to save the state of an execution, or the execution state of a process. Now, what this means is, like in this, the execution state, I got confused. The execution state of a process can be one of these, okay? So what it means is it tells you what the process is currently doing, okay? It can be in a running state, meaning that it is currently using the CPU. It can be ready. What this means is, it if it is assigned to the CPU, it can use it, okay? But at this time, someone else is using the CPU, okay? So this is it's in the ready state, or it can be waiting state or sleeping state. In this case, the process may be waiting for an event. It can be waiting for a timer go off, waiting for some data to be read from the disk, waiting for some data coming from the network and so on, okay? And in this case, this is different from the ready state because in the waiting state, even if you give the CPU, even if you assign the CPU to the process, it cannot use it because it's still waiting for something, okay? And as the process continues, it basically moves between these states. So this is a simple version of this processor state transitions. So initially, like when a process is first created, well, it's created and it is put into the ready state, meaning that now it is ready for execution. But if it's in the ready state, it doesn't mean that it will be running immediately. Now we have this running state. When it's scheduled to run on the processor, then it's switched to running state. And in this state, it starts executing instructions, okay, like here, and then executes, etc. And after some time, for example, it's time now. It's time to context switch to another one. It's unscheduled, and now it's put into the ready state again. Okay, so it goes back and forth as such. And but sometimes when you run, then you need to make an IO, or maybe you create a page fault. In that particular case, then the process is moved into the waiting state. In the waiting state, it has to wait for some external event to be done. It can be, you may be waiting for a timer, you may be waiting for an IO to be done, etc. So and when it's done, then it's completed and you're back into the ready list. Okay, and it moves on in this here until you either it exits or it's killed and hence terminated from here. Okay, and in real life, actually, the life of a process is actually very similar to the life of a student on the campus, which means that it's basically moves between back and forth between these different states, and we will see that. That's a good question. I suggest that you wait for this like next week, okay, in which we start covering threads, and then things will become very clear. That's an excellent question, but just wait a bit, okay? All right. Any other questions? No. Okay. So now we have a structure called process control block, okay? And a process control block is the structure where we save the state of a process and restore the state of a process to again execute back on the CPU. Okay, and this essentially stores these three components of the process, meaning address space, CPU address space, CPU state, and operating system resources. Okay, so these are these three things. And the PCB, which is not printed control board, right? The printed circuit board is contains things like process ID. Every process have a different ID that's assigned to it at the time of creation by the operating system. A user ID who is running it, its execution state, like ready, running, waiting. Its CPU state, the saved CPU state. For example, what are the values of the CPU registers last time when the process was suspended? Because we need this because you have a process that's running, and a lot of temporary values in the register. So when we want to save this, we need to save this in a structure, and this is where we do this. And other things like operating system resources, what are the open files, where's your location in that file, network sockets, and all the other things, plus memory management information such as where is your for example page table, okay, and etc. And scheduling priority, which we will be covering later, accounting information, and etc. etc. So this is, for example, you can see the process control block in Linux, which is, say, structure called, task structure like this, okay? And in here, you can see that, you have this state that's runnable or like stop and etc. And we have a lot of different details, but I'll just go over some of them. And what we have is, for example, things like kernel stack and the process ID and the user ID, group ID. What else do we have here? Let's see. The file system, open file system. This is part of your operating system resources. Memory management information. Okay. And here's the memory management system, for example, the page table, single handlers, and etc. These are all stored in here. Okay. Now, what happens is, the processes are managed by a shared chunk of code, and this is called the kernel. Okay. This is called the kernel. Now, note that the kernel is not a separate process. Like what we mean by a kernel is, it's the code that's run by the operating system, and that's as part of the user process. The kernel is for example, it's similar, but the operating system contains more than the kernel. But without, like, the kernel is the core of the kernel, but then you have a lot of helper application and other things that can be part of your operating system. For example, think of your ls. Okay, the ls executable, which lists the files in a directory, that is part of your operating system, but it's not part of your kernel because ls is actually a user level program that runs here. But the system calls that the ls uses, they are part of the kernel. Okay. Now, for example, think of context switch. The context switch is like it happens between multiple processes. And let's say that I have a process A here, and I have process B. They are both active. Now, so process A, and this is the time axis that's going down. So it's running, and at a certain time, like the timer goes off, saying that, well, now I want to switch to process B. Then when the timer goes off, then there's this piece of kernel code which saves the process state, okay, of process A, which is essentially the CPU state, the address space, the operating system resource. So it saves it in memory or like this, whatever it is. And then it reads the state of process B, okay? It restores that. It restores the CPU state of process B on the CPU. It restores the address space of process B in the memory, and it restores the operating system resources here. And then when it's done, then it leaves the execution to process B. So from now on, then process B's user code is running in here, okay? And then after a certain time, now it wants to switch back. So the timer goes off, the process B is stopped, okay? And then the same kernel code now saves the state of process B here, restores the state of process A, which it had saved, and then runs it here. Note that in the kernel part, this kernel code, that contains the privileged instructions that can access the hardware directly, like the changing of, for example, page table base registers, or changing, accessing hardware like that's directed like disk and etc. Okay, so in this kernel code part, you have privileged instructions as part of your of the instructions, and they will execute in there. In the user code portion, you never have any privileged instruction that directly accesses the hardware. Okay, and it's all non-privileged instructions that are executed in here. Now, here's again the same thing, like in a graphic way. You have process A, it's running, and then we have a timer interrupt, which interrupts your process, every say 50 milliseconds. And upon that, the program counter and everything stays stayed on the stack. And in the kernel space, you can see that at this, when we have this timer interrupt fires, then there's this timer interrupt handler, okay, and we have seen this in this, which is a system call, okay, and this handler is being run, and when it runs here, and as part of this, it will, for example, in this code, it will save the state of the process. And after that, it will then call another one. So in this case, it stores the CPU state saved in the PCB. Then it calls a scheduled routine. Now, what the scheduled routine, again, we have we'll spend 2 weeks on this later. It looks at all the ready processes in the system. Okay, imagine there are 10 processes that are in ready state. So now it has to pick one of them. Okay, it may not be process B or C, whatever it is, and we will see that there are a lot of different policies on this. It will pick one of them. It will say, okay, let's restore process B, and then it will then with this come back to this handler, and then it will restore its state, and then from this on, then the process B continues to run. Okay, so this is a full context switch, basically timeline. Now, these context switches are not cheap. Okay, if you think of it, you need to save the state into the PCB, which, as a matter of fact, when you think of it, you have to save the CPU state, which is okay. It's a finite set of registers, but then you have to save the whole address space, right? Which is huge. And actually, you can guess that we're not actually saving the full state, but we're just changing the page tables, and it will again become clear. And you have to again save the state of the operating system resources, and plus picking the next process and etc. So typically, this is it's not cheap, and in the case of Linux, typically it may take 5 to 7 microseconds, which is equivalent to something like 10,000 CPU cycles. So we basically waste this many cycles just to save and restore the process state from one to another. So the operating system it maintains a set of state queues for each process state. Okay, and one of them is like you can see that the disk is a resource. The CPU is a resource. The network card, it's a resource. So this is and then we have these processes that are basically wants to access them, and the operating system acts who will get what. So the ready queue among this, the ready queue that we have here, for example, contains the processes which are ready to be executed. Okay. Meaning that if I allocate, if we assign the CPU to them, then it can execute. So here is my PID 4277. The state is ready. Here's the PC and registers. There's another process again ready. And for example, for the disk I/O, you want to read something. There may be other processes that are waiting in the queue. Okay, they want to read different blocks from the disk. Again, this is another queue as such. And what we do is the PCBs moves between these queues as their state changes. Okay, and for example, imagine that this particular process, its disk I/O is completed, and if it's completed, then now it's put into the ready queue, meaning that now it's ready for execution. Okay. And for example, in the case of your campus life, again, the ready queue, for example, the CPU can be the öğrenci işleri, the student service, okay? And there's this lady, and there's always a queue behind her. I have been there, I'm sure you have been there sometime, okay? And so the ready queue are the CPU is the lady at the öğrenci işleri, and all these different processes are the poor students on the campus. So the ready ones, when you're ready means you're ready if this lady asks for you, then she can process your job. Okay. So what happens is, she picks one of you, she executes your task, and then she moves on. And then, sometimes, for example, you want to complete your registration because there was some error, etc. But then they realize that, well, hold on a second, you haven't paid your library debt, right? This happens. Then what do? Then you're kicked out of this ready queue, meaning that, even if she waits for you, you cannot do anything. You have to pay your labor debt. And then you have this library queue. Then you go to the library, like the desk, and there's another queue, right? And you wait in there, and then after you paid your library queue, then you're back into the öğrenci işleri queue. Okay, now ready for execution. So this is how it actually happens. Do you have any questions on this? I know you started missing your campus life, but it's that's part of the game. Yes, it will happen. They move between these different queues. There are different versions of this. Again, we will discuss this later in our discussion. So, for example, for the disk I/O queue, we will see that there are a lot of different possibilities, and there is no one good policy or data structure to implement this. Each of them has their pros and cons, and we will discuss them in detail. The same for the ready queue. Okay, I will move on. Now, let's talk about a couple of terms. The first thing is that each process has a logical control flow, which when you left alone, it moves in that one. Now we say that two processes run concurrently, or reach concurrent, if their flows overlap in time, and otherwise they are sequential. So let me give you a simple example. So let's say that we have a single core, meaning that at any time only one process can be used, can be executed. And actually, in the Monday lecture, Onur Hoca has shown the actual, basically, these things, not like such simple things. So process A runs from this time to here, and after that, process B here. There is this, like on this line, there's of course this very teeny tiny context switch, which is I'm ignoring here, okay? And then, process B runs here, and then after that we switch back to process A and then process C. And then, process B ends here at this point, process A ends at this point, and then process C ends here, okay? Now in this location, in this case, process A and B, they are concurrent, okay? And A and C are also concurrent. So when I look at process A's, basically, like from a user point of view, you're not aware of this, like this gaps in here. You see that process A has started here, and then it was active till this time. And process C, it was here, and it's active here. So these process A and C, they are concurrent. This is like, you're listening to your music and also editing your file. They're running, it's switching back and forth, but since you feel that they're active at the same time, they're called concurrent, okay? But process B and process A, they're also concurrent because they are both active. Their time, basically, you can see that it's the same time. But process B and process C, they are sequential, okay? Because, when you look at this time, when process B is active, process C was not active. So this process B ended, and then after that, process C started. Okay, so that's the main idea. And, parallel means something different. In the case of a parallel, maybe I should have drawn the figure in here. Let me see if I can. So in the case of a parallel, let's do this again. Parallel. In the case of a parallel, you can have parallel execution if you have, for example, two cores. In the case of a two-core, like let's say I have core 1 here, and then I have a core 2 here, okay? And if I have a program that's running here in core 1, and this is time, and then another program that's also in core 2 at the same time, then, these two programs, you can say that they are running in parallel, okay? But concurrency is different from, concurrency is actually, you can see that it's an illusion of parallel execution, but it's not actually parallel. Okay? Now let's move on. So how do you create a process? That's a good question. And it's we have a system call to do this. And this is, you can see that, creating a process by itself, it's something that's privileged, right? And the way it works is, this is like in the Linux world, and this is also true in all the main operating systems, is that, you have a parent process, and then it creates, makes a function called fork, okay? And then through this, it creates a new child process, okay? So this is very interesting, and this is the first system call that you will learn. So fork is something that's it's a kind of almost like a miracle, like magical, system call. It's because, like, imagine here, like, I have a process here, okay? And this process at some point in the execution calls fork. And when it calls fork, it makes a system call. And what happens when you have a system call, then this process is frozen in time. Because you remember our library case that, you fill in the form and you ring the bell, okay? And then, in the kernel space, it does something, okay? Now, what does the fork do? What the fork does is the following. It's in the case of a fork, it copies the CPU state. It creates a new process, a duplicate of this one. It copies the CPU state, it copies the address space, and it also copies the operating system resources, okay? And it creates a duplicate of this one, okay? This guy, when it calls the fork, it's still sleeping, okay? So the fork copies this when this process is being asleep, okay? And it makes a copy. Let's say that this is an identical copy, okay? Now you have two of them, and then the fork returns in both of the processes, okay? So this is, in this case, the fork is interesting because it is called once. It's called by this one, which we call the parent, but it returns twice, one in the parent one and one in the child, okay? So that's how a fork works. And when you see this, and then when you have these two copies, remember, they have the very same address space. They are in the same place in execution. They have the same CPU state, and etc. And when they wake up, and then the operating system starts running one of them and then the other one. So then it basically starts executing them, right? And these two guys, they don't know who they are, right? Like, imagine, me, I make a copy of myself, and then and then when I do that, when I wake up, you have no idea you made a copy. Are you the copy, or are you the actual one, or are you the parent? Okay. So to resolve this, the fork system call returns an integer as its return value, and it returns 0 in the child process, and it returns the child's PID number. Let's see. PID number, which is greater than 0. Okay, it's greater than 0, non-zero, and to the parent process. Okay, so the parent process, when the fork returns, it gets the non-zero PID of the child process. The child process, in child process, it returns 0. The fork returns 0. Okay, that's it. So this is, again, now let's think about how it works. So here's the very simple case. In this particular case, so we typically use this. Let's see here. What's wrong key? Okay. So this is where you make the function call, the system calls a fork. Okay. Now at this time, when you call this fork, the program starts execution at this line. Okay. So here, it stops, okay? And when it stops here, then this whole thing is duplicated. So imagine that, I have a duplicate of this. So this is called the parent, okay? Now everything is duplicated. The address space, the CPU state, the operating system resources, they're all duplicated. And now I have a duplicate of this one, which will be called the child, okay? And in here, now again, I have the same code. I have this for code, right? So just do this, okay, for, okay. And then, it's here. So PID is here. So at this point, what happens is, then when both of these processes, the parent process and the child process, they are both inserted into the ready queue. And then after that, then the operating system starts executing one and then the other one, okay? And it depends who it executes first. But when it executes the parent, then the PID here, this will be the PID of the child. Let's say that the child's has a PID of, say, 11, okay? Non-zero. So it will get, in the parent case, it will return 11. In the child, the PID will get a 0, okay? So from this information, then in your code, then you can diverge in two different flows. For example, in this code, you can say that if the PID is equals 0, and in this case, since this is the parent, then this will fail, and you will go here and you will execute this parent code. So you will print the parent here, okay? Whereas in the case of the child, now if PID is equals 0, again, you have this code here, if PID, okay, equals 0, and in this case, okay, in this case, it will be true. So this code will be, if part will be executed, okay? Now, when you run this, for example, you can write this code, you can just try it, and you will say that, it's like in this case of the parent decrements it to 0, whereas the child increments it to 2. So you will say they will print like that. And then here, if you run the same thing again, then maybe this time the child will print first and the parent will print second, okay? One again, maybe again it will be as such, and etc. So why does this happen? It happens because when the operating system, when it picks up a process from the ready queue, you have no control. It can be picking up any of them. And what the fork does is it duplicates the parent process into a child, and then it inserts it into the ready queue. Now in the ready queue, you have the two copies of the same process, but they are not aware of each other. They all think that they're the same. The only difference is their PID return values here, okay? Now let me move on here. So let's look at, again, the same code. So here we have, when we do this, note that the address spaces are copied, okay? Meaning that they are no longer in the same address space, and we can test this in here. So here's my child code, okay? In the child code here, you're incrementing as like this, and in the parent code, then you're decrementing. But what you would see here is the parent's x, okay? It goes like the 0 and -1, and whereas the child, it prints 2 and 3. So they actually, the fact that they're duplicated means that, after duplication, they now have different values. You have another x in the child, another x in the parent, okay? So after the fork, both child and the parent have a separate life of their own. They're completely disconnected. They are not aware of each other. They cannot intermingle with each other's data structures. Now, when we have this fork, we will model them like when things fork, then all of a sudden you no longer have a linear execution flow, okay? But now we have like things that basically forks, okay? And you create a new execution flow, and then then you will have the scheduling that switch back and forth. So we will use process graphs. We will use process graphs, okay, to model this. A process graph, it's something it's a tool to capture the partial ordering of statements in a concurrent program. And this will become clear. So in this case here, each vertex is an execution of a statement. A arrow B means A happens always before B, and we can label edges with current value of variables, like printf vertices can be labeled with output, and each graph begins with a vertex with no in edges, okay? And any topological sort of the graph is corresponding to feasible total order. Now let's see an example. So this is this is a process. So this is a process graph for this particular program, okay? So in this case, you can see that like initially, x equals 1, okay? So this is the first, this is the parent, the lower line, and this is the parent. You initialize x equals to 1. And after this, then you call fork. This is a vertex, okay? And after fork, then you have a child. It has a separate line of execution, okay? In which then you print, and then you set x equals 2, okay? And then exit. And then this is where the child terminates. And here I have the parent. So after fork, then it will again execute printf. This printf is actually this one, okay? But whereas this printf, okay, that's the printf that's print here, okay? And then it exits. So in this case, you can note that now let's go over this. Each vertex is the execution of a statement. Also, we start with the first one, and you can say each graph begins with a vertex with no in edges. So there is nothing that's coming in here. It only has outgoing edges. Okay. And then we have each vertex is the execution of a statement. For example, this vertex is the execution of a fork. This vertex is the execution of a printf. This one is the execution of an exit. Okay. And then when you have A to B, it means that A happens before B. For example, if I have an arrow here, and this edge here says that fork happens after you start with the main, or printf here happens before fork, and exit happens before printf. Okay. So and then on the edges, then we can have this current value of the variables. Now you can see that after this time, after this fork happens, now you have the child here and the parent is here, and among them the execution can now vary. Okay, you don't know whether after fork whether the child will be executed first or the parent will be executed first. So we have really no idea. So let's take this original graph and let's just label them A, B, C, D, E, F, okay? And in here, then you can have we have a lot of different ordering keys. Now in this case, we see that B always happens after A, okay? So you have, so we have this constraint, okay? Let's see. And then C happens after B. Okay, so you can have this one. So you can see C is here. And then after C, then we can have D. On the other hand, E happens after B. So this is, from B, I have a marking to E. And then F happens after E. Okay, and it's here. Okay, so once you have this, now you can see that there is some ordering. It means that there is not a total ordering. But from this, you know that since there is no loop here, F cannot happen like before. So sorry, in this case, if you have like in this case, if you have a total ordering like this is infeasible because it says that F happens before E, which is not true in here. Now let's look at this, very simple example in which we fork, we print L0, and then we fork, and then we print L1, and then we fork again. Here's a question: how many processes will we have in the end? 8? Wrong, but good try. Yes, exactly. It will be 4. Now let's look at this. So here's my main process, main parent process, okay? So here's my initial parent. We have a fork. After fork, now after this point, now we have 2 processes, right? And they will both print L1, okay? So in this case, this is the child of the first one, and then this is the parent. And after that, well, the parent will fork again, and it will create a second child here. And then it will move on. Whereas the child here, now it becomes a parent by forking again, and then it will print by at the end, okay? So you can see there are 4 processes that are created by this. Now in this case, when you look at this, when you run this, you will see that they will be printing in different ways. For example, like L0 will always be printed first. L1 by, L1 by. Now, is this a feasible output? Because, since we have this partial ordering constraints, there is no single output like this. There can be multiple printouts that you will see each time you run, okay? But some of them, and then, the feasible ones are the ones that are basically obey these partial ordering constraints. So let's look at this feasible output. It says it prints L0. So this is, of course, it's just L0. And then afterwards, if it prints L1, well, we don't know which L1 it is, but let's say that in this case, this L1 is printed. And then we move on, we execute this one by, okay, and then we execute this one, another by here, 2 bytes. And after that, we context switch to the first child. We print L1, and then after that, we print by, and then by, okay? So this is a feasible output. This is something that we expect. What about this? This is an infeasible output. Can anyone tell me why this is an infeasible output? Exactly. So we know that there's a lot of freedom in here, but in this case, a by should always be preceded by an L1, okay? So you cannot have this. If somebody says, well, my program has printed out this, you know that there's something wrong with this, okay? And this is something that you will do, for example, when we give assignments, in which involve such forking. We cannot say that the output is this string. There's a lot of possibilities, so we have to check for all these things. And sometimes, if students want to, cheat on this, and then they may hand it this infeasible output as a way. But this is fairly easy to check. Yes, exactly. So when we said there's this partial ordering and total ordering. So the total ordering, there is some based on this partial ordering constraints, there are a lot of different global ordering possibilities. Okay, so that's basically it. So if you do not have any further questions, let's have a 10-minute break, and then we'll continue after the break. Okay, let's see. So now let's look at some nested forks in parent. Okay, and in this case, now when we will fork, but it will be slightly different because when we look at here, it says if fork not equals to 0, okay, then, who will execute this printf this code? Will it be executed by the child or the parent? Any guesses? Exactly. So always keep this in mind. It's like, the return value of fork, it will be 0 in the child, and it will be the PID of the child in the parent. So the parent will know its child, but the child has no idea who his parent is. Okay. And again, now, so you will see that it will go here, and then we'll have another if fork is not equal to 0, and so on. Again, when you look at this, it looks complicated, but that's why we need to have this process graph. So here's the child. Here we see the L0 here, and after fork, then the child will skip this here. After this fork, the child will skip, and this by will be printed by the child and exit, and it will exit. Okay, and then the parent will print L1, and after it will do another fork, and after fork, then you can see that the parent will continue to L2, but the child will exit here and will again do this by in here, parenting, and then this last by here will be printed by the parent. Okay, and with this, then you can now talk about the feasible outputs. You can see that with this partial ordering constraints, L0, L0 is printed first, of course, and after that, L1 is printed, but maybe, before L1, by can be printed as well. Okay, you can see that. So now after L1, then by can be printed, and by looking at this, you don't know which by it is. Like, it can be this by, or it can be this by, right? They're both possible. And then another by, so again, we have no idea. And then after L2, then another by exits. But when we look at here as an infeasible output, you can see that after L0, well, a by, well, yes, it's possible, right? In this case, it's a by is possible. Let me just do this. Okay, so here after L0, L0 is here. Then we see by, we said, well, this can happen, possibly. And then L1, yes, then we continue executing this one. And after that, a by happens, well, this can be printed. But then, hold on a second, here we have a problem, right? L2 should precede by, and hence this is an infeasible output. So here is another again fork example. In this case, who will be printing this code, child or parent? In this case, we'll be going with the child. So you can see that in this case, the by part will be printed by the parent, whereas the child continues with L1 and then forks, and then the child, and so on. Okay, so it's the same thing, and we can again talk about the feasible and infeasible outputs. Okay, so you want to write a code that will tell you, return how many processes has been created, right? Well, it will be a little bit tricky because you have to, like once they are created, for example, once we have this child here, then even if you keep this parent alive, it will have no idea what this guy will do. So there will be no single process which will tell you, how many active processes that there are in the system. It's only at the kernel level where it keeps a track of all the processes, so then you can see that. But what you can do is the following. For example, when you have a child, well, we'll see. Like, let's go and see how with a couple of other things, and then you will see that we can have some coordination between children, between child and parents. Okay. So now let's see, like this idea of a fork is actually interesting. Why do we make a copy of the parent process, right? Why don't we just create a new process initially, right? It's like, let's just create process. Well, first of all, like, cloning can be handy in a lot of cases. For example, in the case of a web server, what happens is, there's this, the web server sits and it waits for incoming network connections. Okay, when it receives a network connection to serve a page, then it forks. It lets the child to handle this, to serve this page, and then it's still now it continues to wait for a new process, a new request. Okay, so once this guy serves this one, it disappears, but the parent always stays there. Okay, so that's really good. It's you set up this initial state, and then you fork off multiple copies to basically do your work. It's it will be really nice, as students you are that like each at the beginning of the semester you have only say one person, like I say one Fatih, okay, and then when you as you add more courses, you just fork yourself. Fatih, the first child, the second child, and then they will continue to do the job, and then you just wait there, and as you register more, and when a new course comes, you just fork off another copy and so on. Okay, so in the Unix philosophy, there's the main thing is the system call should be minimal. And recall that the whole Unix was developed by just two guys, and which I'm hoping that you have read the reading assignments, which I will check in the quiz in the that it was just written by two guys, and they want to keep things minimal. So they don't want to overload the system's calls with extra functionality if it's not needed, and try to provide a flexible set of simple primitives and let the programs combine them in useful ways. And of course, when you have these forkits can get out of control, and if you have seen the Matrix 2, right, the idea is the following. It should do only one thing, okay, and then it should do it well, and then you should be able to combine them to do multiple things. I mean, take the case of, for example, in your kitchen, you have a knife, right? And then with the knife, well, it's a very generic. You have a knife, fork, and spoon. Okay, and with them you can do a lot of things. And sometimes these guys, for example, sell you, for example, if you have to squeeze a lemon, they sell this nice tool, okay, that plug in and then you get the juice. That's one way, right? And, the idea is, for example, in the case of a lemon, if you don't, even if you have that complicated thing, you can just cut it up with the knife, and then you can use a spoon to extract the juice. Okay, so once you have this minimal set of cutlery in your kitchen, then you can do a lot of the things. You don't need those fancy things. Okay, of course, those fancy things may be useful in certain settings, but you just be minimal and let the let the user basically use them, combine them in any way that it wants. So if you have watched the Matrix, I think this is from Revolutions, then you can see that Mr. Smith had many duplicates, and this is essentially what you call the fork bomb, where you can just fork over and over, and you can see that this goes exponentially, and then your system, typically in operating systems, there's a limit to the number of processes that you can create, so it will say it will stop you, but you can imagine that the same thing happens, right? Now, when you do this, there's this, one of the things that you will realize is when you fork, you'll be amazed how fast it returns, okay? It will be returning like this, okay? And you will say, hold on a second, I mean, it's supposed to duplicate three things, right? CPU state, which is fine, but the address space and operating system resources. And duplicating them is huge, right? Like you have to duplicate and create a duplicate of the whole address space because you just have another copy of this. Now, in this, when we have you will see that again, this is something we will learn later. When you copy the new address space, for example, in this case of when you do a fork, okay, you're supposed to get two separate copies of the same address space, okay? But actually, they do not actually get this duplicate, but there's an illusion that they continue to share the very same physical memory until one of them makes a change. So it means that, when you are duplicating this memory space, its physical memory usage is not duplicated. They continue to point to the very same physical memory pages until one of them makes a change, and then it will be duplicated. And we will see that particular one, which is copy on write, later in the semester, but there's a lot of tricks behind the hood. But conceptually, it's duplicating the address space. Now let's move on again, let's look at other system calls. Now here's the second one, which is called the exit. Okay, so this is useful for terminating a process. Okay, and a process becomes terminated due to one of these three reasons. First, it may be receiving a signal whose default action is to terminate. For example, when you press Control C to a program, and its default action is to terminate that process. Or sometimes you send, kill, -9 to that process ID. Again, you're sending a signal to kill it. The other options are, you may be returning from main routine, or you may be calling the exit function, at any point in your program. So typically what it does is you exit, and there's this status, which I'm pretty sure you have not used, right? Okay, and you have no idea. I'm dying. What am I supposed to return? This status. Well, guess what? And usually the convention is the normal return status is 0, and it's non-zero on error. Okay. Again, what this means is, this is again another system call that the exit is called once, but it never returns because, by its return is to terminate the process. And, again, there's this function called @exit, which actually registers the functions to be executed upon exit. Okay, and so you can use them in your code. Now, this value that we return in the exit part, okay, this status, will actually be used as a form of communication between the parent and its child. Okay, so this is called the reaping of child process. Now let's see this here. So when you have a process, when it terminates, it still basically consumes some system resources. And what this means is the following. When you have a child and here's the parent and here's the child, when the child exits, okay, its return value can be passed to the parent if it's waiting for it. Okay, for example, this you can see in your shell. In your shell, what you do is you can see that the shell is a process. Then you type in a command, which is then another executable. When you press enter, then it creates a new process with that one. And when this one exits, then you can get how it's returned. If it's a normal execution, it was killed, and etc. So this is a form of thing. And when a process terminates, its exit status should be passed, and as well as the various operating system tells. And if it's not, basically, if it's not reaped, it's called a zombie, meaning that it's not alive, but it's not also dead. Okay, so what we call reaping means reaping happens by the parent. It's performed by the parent on terminated child using wait or wait PID system calls. And through these system calls, the parent can get the exit status of its child. Okay, and once it gets it, then the child process is put to rest and disappears from the system. Okay, so this is a very interesting case that you create a child, and then when the child exits, it returns a value. Now this value needs to be picked up by the parent, okay, and processed, and after only that, then the child completely disappears. If the parent does not reaps or does not get and processes that status, then it remains as a zombie, meaning that it's not using CPU, but it still remains kind of alive in here. Okay. And you will see that, if a parent terminates without reaping a child, and then the orphaned child will be reaped by the init process, where the init process is the first process in the system, which PID equals 1. So initially at boot time, you have this init process. Let me see if I have. Okay. So initially you have this init process, which is created from scratch at boot time. And all the other processes are forked from this init process. Okay. So you have a tree of processes. Okay. But everybody goes back to this init process. So you can see it's, Adem and Hawa in one batch. Okay. And if a child remains orphaned, then it will be read by this init process. So let's look at some like a zombie example. So here is again, here we have a fork, we execute fork, and this is the child code, and this is the parent code, okay? Now the child code terminates, prints this, and then exits with a return value of 0. Whereas the parent code, it's running, and then it gets into this infinite loop, and it never exits, okay? Now when we run this, you can see that like it runs here, and it prints like in this particular case, it's running. The parent is said that it's, you can see the parents when we run this, it is a PID of 6639. The child has 66440. Okay, and now after this, the child has terminated. But when you look at here, you can see that you will see the child, this is the child, as in this defunct state, which is the zombie. Okay, so it still remains there, it's not consuming any time, whereas the parent, which is this one, it still is active. Okay, and when you kill its parent, okay, then then the init reads the child, and then after that the child is removed from your PS list. Okay. So here's a non-terminating child, for example. In this case, again, this is the child code, and this is the parent code. The child now is in infinite loop, and then the parent exits. Okay. Now what will happen? So again, we have the child and parent created. And after that, you can see that the child process is still active, okay, even though the parent has exited. Okay. So after this, if you then you have to kill the child explicitly like this. Otherwise, it will keep running until you shut down. And here we now kill, and now it disappears because since its parent has already died, it's now read by the init and hence put to rest. Now, for this, for the parent, we have this wait system call to read a child. Okay. So it says this simple thing, is called wait. This is used by the parent, and then in here it reads the child's status. So whenever the child exits the status value, it will appear in here. Okay, and it will suspend the current process until one of its children terminates. So here's my parent process. And when I call this wait, which is a system call, which is implemented as a sys call in the assembly, right? Then it creates an exception and it will wait. It will wait until one of its children. It's not waiting for a specific children. It's maybe it called this wait after forking many children. Okay, it's 100 children. But when you call wait, it will the first child that terminates, it will get its that, and then after that it will return and then continue its execution. Okay, and in the meantime, like when we do so in this child status, okay, so when you call this, it's suspense, meaning that the parent process is no longer getting anything. This is something, for example, when you run an executable in your shell, okay, you run it and then your shell disappears until your child process, the program that you're running, exits. And after that, you get back to your shell, right? This is the same thing. And here, the return value of this int, this is the PID of the child, okay? This is the PID of the child. So it not only, so this status, it tells the parent, how did the child die or terminate? Was it killed? Was the normal execution by returning different values? You can do that. And this says that, and this value, the return value here, it says the PID of the child who terminated is this, because you may have multiple children, okay? And there are certain macros defined in here, like whether if it's exits, if it's signaled, whether it receives the stop signal, whether it's continued, whether it receives the term sig, which is control C. So you have to read all these different details in the manual. So with this completion status, then you can, once you have the status, then you can use this macros, like we've exited, and it returns a non-zero value if it's terminated normally, okay? If exit status, it's true, all this, and the macro returns the low order 8 bits of the exit status. This is, for example, if signaled, returns a non-zero value if the child process is terminated because it received a signal that was not handled, okay? Or core dump, for example, it returns you can check this whether it's terminated and produce a core dump and etc. So this then you can use to analyze make the post-mortem analysis of your child, okay? Now we can use this wait to synchronize with the children. And here's an example. So if it's 0, now this is the child code, okay? And this is the parent code. So the child says, hello, and then it exits, and here's the parent, it now says hello, and then this is basically, it says wait for the child status, okay? It's not taking care of the input, the return value of wait, because, well, it didn't care which child it is, okay? So when you do this, then it has to wait for this child to exit before printing this one. So let's look at the process graph for this. So we start with fork, and here's the child. It prints HC, hello, from child, and then it exits, okay? And with the parent, it prints HP, which is here, and then after that it waits. It waits until the child exits, okay? And only after that, it will print CT, which is child has terminated, and then by, and it will exit as such, okay? So you can see that by this wait created this extra dependency, and you can use this to control the execution, to synchronize the execution flow between the child and the parent, okay? So in this particular case, again, a feasible output would be, HC, which is here, like HC, and then HP here, okay, it's done, and then CT and by. So this is fine. An infeasible output would be, for example, HP. Let's do this again. In this case, HP, you can say, well, yes, we can start with this one. And then CT, no, this cannot happen, because for this to happen, HC and exit should take place. Okay, hence this is an infeasible output. Okay, another one. So here we have another wait example. In this case, the parent creates hundreds, creates n children. Okay, so in this case, it's reads and it puts their PID IDs into here. It creates it forks, and you can see that this fork is happening. This is the parent code. Okay, so it's always the parent that's forking, and then it let's see here, and then this is the okay. So in here it forks 100 times, but let me just do this. Okay, so this code here, okay, so this loop that I have here, this is running in the parent code, but this code, the exit code here, this is running in the children. Okay, and so it forks n times. It stores the PID values of the children in this PID array, okay? And then with each of the children, then returns a value with this index. So the first children returns 0, the second one returns 100, and sorry, the first children returns 100, the second one returns 101, and so on, okay? So this is, and then it exits. And then the parent, after creating them, again, this is the parent code. And then it says it gets into this wait loop. And it says, I will wait for my children, and I will look at their status, and I will get the PID of my child. And what I will do is, for each of this, like each time, remember this loop will run n times, okay? And then you will check it will check the child status and basically how it's returned here. And if, for example, it exited normally, it's fine, which is returned by this exited. Otherwise, which is an abnormal termination, then it will print this. Okay. So this is like this is a way, but in this case, note that when I have these n children, who will execute when and who will execute in what order? This is completely undeterministic, non-deterministic. Okay, so they will exit at random times, but with this one, it will basically return in their order. So you can, by running this, you can get, you can print out the order of your child's exit. Now, sometimes what you want to do is you want to wait for a certain child to exit. And this is a case where you use the wait PID. In this case, you say that I will be waiting for my children with a certain PID. Okay, and here's the PID. And then here's when you fetch its status, and this is, and then we have options, so I'm not sure what that includes. So again, this is the same code where we create n childs here. Now, what I do here is wait PID, and you wait for the first children, okay? And you wait for the first children to exit, and then you print them here. And then you wait for the second children to exit, and then print them in here. So in this case, when you see here, the parent here, the PID, will be printed in the increasing order, okay? In the first case, in the previous case, they will be printed in random, basically, order. Whereas in here, now in this case, imagine that, I have, say, 5 children, okay? I have 5 children, and say the fourth one is terminates, but still I don't return, so what it will do is it will remain in the zombie mode, okay? It will return its value, but it will remain as a zombie. And then, maybe the second one, it will remain as a zombie. And then the first one, when it exits, then this wait PID will return, okay? Prints it, reads it, and it will exit. And when it comes back, now this one has also returned. So it will reaps it, comes back, returns, and so on, okay? So this is the main difference between wait and wait PID. Any questions on this? No? Okay. So let's move on to other exciting system calls. This is called exec, okay? This is, it's called the exec. We will just look at the VE version. You'll see it's a whole family of things. So this is what you do is like so far when you look at fork, it looks useless, right? When you fork, you make a copy of yourself. And you know what most of the words like take a shell. A shell, it forks a new one, but this new guy, the new children, you want him to make him something else. Okay, a new process. So the execv does that. It's when you run execv, it gets an executable. Okay, this is the path for the executable, and it gives you the arguments and the environment. Okay, parameters, and with that, then it will loads and runs in the current process. Okay, so here's the file name. This is the executable. Okay, and it can be an object file, or it can be a script file that's beginning with this. And then we have the argument v, which is the you know the arguments that you'll pass to this executable. And by default, the argv0 is the name of the file. So this is kind of useless, but this is the convention. And then we have an environment variable. The environment variable is essentially when in your shell you have this name and value strings such as the user this, the printer is this, the PTY is this, and all those things that you will see. And then this is where you pass them through that parameter argument. And what it does is it overrides the code data stack, but just retains the PID, open files, and signal context. We will see this again. Again, the execv, this is called once, but it never returns except there's an error. So now you can see that how we see things. Now, if you want to fork, but you create a new process, that what you do is you should fork, and then you should run execv. Okay. Now execv, note that execv, it does not fork a new process. What it does is it replaces the address space and the CPU state of the current process with the new one. So it loads the new address space from the executable file and then starts from the main. And then, to start a new program, then you have to, what you have to do is you'll use fork and then follow it by execv. So we will see how this works. And you can see like similar action in the matrix as well. So with the exec, again, as I said, there's this, a whole set of exec functions, which I will give you a list. It's loads and runs an executable at this particular path with arguments arg0, arg1, etc. And here's the environment variables and so on. Let me just go ahead. So let's look at here this simple example, how we work. So this is kind of similar to what's happening in the shell. Okay, in here you can see that now I do a fork. Okay, and now this is the child process. So this is the parent part. In the parent part, it says I will wait for the return value of the child. So parent runs creates a new process for the child and then waits. And this is where all the action happens. This is where the child is working. And in this case, it starts, okay, it prints this, okay. And then, then we call the execv here. And we call the execv with these things. So here's why bin echo, okay. And bin echo is, this is a simple program which prints its arguments. So when you say echo, say Alishan, then prints Alishan. It's echo, Filiz, and it prints Filiz. Okay, it looks like it doesn't do anything, but this is one of those again minimal utilities in the Unix version. So this is the executable of this echo one, and you can you can put your own executable. Okay, and then you put the arguments. And the arguments here is again, like you have an array, And with at the zeroth version, argv or new arguments, this is the name of this. This is actually, it's a convention. It's not recurred. Even if you leave this empty, it will work fine. This is just a convention. Okay. And then with the echo, and then you have your some random string, and then you put a null to indicate the end of arguments here, and you pass this as the second one. And you don't use the, we're not using the environment variables parameters here. Okay, so we fill them here, and then we run execv. Okay, now when when you run execv here, something happens. Like this is like imagine I'm here. Okay, and what I do is like at this time, like let's say forget about fork. Okay, if I'm here and if I say execv Brad Pitt, okay, Brad Pitt, and then these parameters. And when I do that, when I make the system call, what will happen is, can anyone guess what will happen to me at that time? I'm going to be Brad Pitt, but how old I will be? I will be a baby. I will be a newborn Brad Pitt. Okay? And there will be nothing left for Aerology. Like Aerology is gone. The whole address space is deleted. My executable is replaced by Brad Pitt, and from the very first line of main. Okay, that's why it's like it's a newborn Brad Pitt will replace me. Can you get me back? No, unless Brad Pitt calls execv arrow. Okay, in which case then I will be created, but as a baby arrow. Okay. But when you do an execv, it's changed immediately. When you run execv, the process that executes is gone. And that's why, for example, when you look at here, I said that if the execv returns an error, when will it happen? Like if this executable, it does not exist in the file system, then it will print this. But otherwise, if it's fine, then, for example, this portion, these two lines, they should never get here. They should never get printed. Okay, because it's overwritten. This portion of the code is gone. And so this is again a very interesting thing, right? And in here you can see that this is the code. This is it exits 42. Do you know what the meaning of this? Anybody know why we have 42 here? Yes, the Hitchhiker's Guide to the Galaxy. Yeah, exactly. Yeah, you know that it's like there's this planet-sized. Let me tell you the story. I think there's this planet-sized computer which is supposed to answer anything that you ask. So some guy like this, I think this is the hitchhiker. He goes there and he says, like he asks following question. He says, what's the meaning of life? And so the computer says, okay, I'll think about it. It thinks and then thinks, and I think like a long time. It says, okay, I have to answer. And it says, what is it? It says 42. And then it says, well, what do you mean by 42? And then the whole giant computer says, well, okay, let me think about it. And then it goes back to and thinking. Okay, so that's what 42 means. Okay, so it has this funny story, and this is also the plate number of Konya, where I'm from. Okay, so it has this nice link, Konya linked with Hitchhiker's Guide of Galaxy, and etc. So let's move on. So as I said, the exec, there's a whole function family with different formats, and as I said, I've shown the execv. But like you can say, the LB is saying that the arguments are passed as an array of strings. L is saying the arguments passed as a list of strings to here. P the path, E the environment can be specified later by the caller. So you have all these exec versions. You can see that by looking at them, you can use different versions. But in their essence, it's always it always does the same thing. It's just the parameters that are changing. And with the environment variables, well, just to clarify as a side note, An environment variable is basically it's a dynamic named value that can affect the way running processes will behave on a computer. Okay, so they are part of the environment. Okay, and things like, for example, you may have a temp environment, like temp variable, environment variable, which tells you that where to store the temporary files. Okay, for example, in your shell, you may say that, well, the temp is /temp, so it means that any program that you run, if it inherits the same environment variables parameters, then it will use this. It will store its temporary variables in that location, or the home directory. Okay, or the user profile, and etc. So you can use printf in your shell to get the full list and set this as such. So as I said, in the case of Linux, and this is also true for most other Unix-like operating systems, the first at boot time, the init, this is the first process that's created at boot time, and after that, you have all these different processes that are forked and then followed by execs. Okay, and you can see this with the ps3 command. And here's some daemons, login shells, and we have child, and etc. etc. This is how it goes. So to summarize basically the whole topic, well, we have learned about a process. A process is an instance of program in execution, meaning that it's different from a program. From now on, if you mean a process, say it as a process. If you write a program, it means that you have not learned it. So this is very important. And in the case of a process, if you want to save and restore its state, you need to store like three things: CPU state, address space, and operating system resources. Okay, and at any time, a system can have multiple active processes, but if you have a single core, only one of them can be executed at a time. If you have a dual core, then we can say only two can execute at a time. Okay, and each process basically thinks that it has its own processor, it has its own private memory space. And so we said that we will use fork to spawn processes, and this is a system call which you make one function, one call, but two returns. And the original one is called the parent. The fork will return a non-zero value, which is the PID of the child. The child in child, the fork will return as 0. Okay, and then we looked at the process completion, which is through exit, and this is again, it's a call. It says no return, and its status is returned with this one. And for the processes, their return values need to be read by the parents, ideally, and this you can do with wait or wait PID. And if you want to load and run programs, then you have to call exec, some variant of this, which is again, when you do this, you make one call, but it doesn't return, because after this exec system call, then the whole address space and CPU state is cleared, and basically the new process is loaded. Okay, so that's it for today's lecture, and if you have any questions, I can take them now. It doesn't, like the wait, when you do a wait, it will wait for one of its children to terminate and return its value. That's it. It doesn't wait. But the operating system, like you have seen that tree, right? In that tree, then you can, I think it can keep the parents, like who is, if you have a children, it also keeps track of who is the parent, so that it can pass it to its children, so to its parent. Okay, so that's it for today. Unfortunately, I had a problem with the quiz, so it didn't happen today. Well, I hope you enjoyed the lecture, so I'll see you next week.